Okay, here we are in Chapter 1, and these two slides are talking about dispersion and pulse spreading. So Chapter 1 gives us an overview of the entire subject, and here's an introduction to dispersion and pulse spreading. One thing we mentioned in a video earlier is that part of the desirable characteristics of optical fiber is to have a good frequency response. And what we meant by that was that it had low dispersion. And so dispersion is the limiting, is the propagation speed dependence on the wavelength. So any source that we have will have a spectral width. Okay, and this contributes to a difference in propagation speed amongst those different wavelength components of that signal. And what it does is it causes pulse spreading. And by causing pulse spreading, it limits the bit rate. So dispersion limits the bit rate due to pulse spreading. We can picture pulse spreading very simply here in sort of a cartoon picture where we make sort of a narrow pulse, maybe representing a 1 in a signal, in a digital signal. We're going to put that pulse into our fiber, that's our channel, and out the other side is going to come that pulse, but that pulse has now been spread out in time. And we can characterize that with a pulse spreading parameter, delta tau, and maybe we call this time t, say for the bit period, and then on the output side our pulse is now t plus delta tau wide in time. So it is spread out by the amount delta tau. And so delta tau is our pulse spread. And what that does is, so here's just a single pulse being spread out. Let me take a signal, and I'm going to have two different pulses here. I'm going to have two different pulses representing two ones in my signal. And this may represent, for example, a 1, 0, 1 binary signal. Well, when I put those pulses into the channel and they spread out, what we're going to get is we're going to get sort of a mixture. So those two pulses are now spread out, sort of like this, overlapping one another. And at this point, you don't know for sure what you've got. Maybe you see this is 3 ones in a row, for example. So these two pulses, I've sort of drawn them as each spreading out more or less independently here. And this delta tau then is our pulse spreading. And this causes inter-symbol interference. Also known, abbreviated ISI. Okay, so this inter-symbol interference limits the bit rate of systems, and you can see here, and we'll talk about this in Chapter 3, that as soon as the pulse spreading gets to be about on the order of the time for a bit period, then we're having problems. So if delta tau is on the order of t bit, then we start seeing inter-symbol interference, and the bit rate goes up dramatically. Okay, so that's sort of the basic idea of pulse spreading. Pulse spreading is proportional to the distance L that we've gone in the fiber, so it spreads a little bit, and as it propagates down the fiber it spreads out more and more. And what happens then is that because it's proportional to the distance, we can either have a long distance and we'll have short pulse spreading, or we can have a short distance, a short distance of fiber with very little pulse spreading, or we can have a long distance of fiber with a lot of pulse spreading. Either way, our bit rate is limited, and it turns out that pulse spreading limits the rate distance product of our fiber. Okay, and so we have an R, a bit rate RB times L is more or less a constant. So we can either have a high bit rate over a short distance or a long distance with a lower bit rate. Okay, so there's a trade-off between bit rate and distance propagated in the channel, and that's a result of signal dispersion. The pulse spreading has a number of different possible causes that we'll study. The first is material dispersion. It turns out that the glass itself, that is silicon dioxide, has the property that the index of refraction depends on the wavelength. So N is wavelength dependent, and the index of refraction, as you should know from your undergraduate careers, but the index of refraction characterizes the propagation speed of light in the transparent substance. Okay, so first of all, we've got material dispersion. The material itself has a wavelength dependence on the propagation speed. We also have waveguide dispersion. So we have a waveguide property and we characterize the behavior of the waveguide with what's called an effective index. So N effective characterizes the propagation of a mode in the waveguide. We'll study these in Chapter 4 in detail. And the N effective is also a function of the wavelength. Okay. Finally, well, another one is multimode distortion. It's not called dispersion, and Peleus, the author, makes a careful distinction there because it's not a wavelength dependence, and so it's not a dispersion property. It's a distortion. It's a distortion of pulses due to the multimodes propagating in the fiber, and each mode propagates with a different propagation velocity. So the index, the effective index of mode number 1 doesn't equal the effective index of mode number 2, and that's not equal to the effective index of mode number 3, etc. Okay, so a single pulse may actually propagate in multiple different modes in that fiber, all arriving at the output at different times, and that distorts the pulse as well. Finally, there's a property called polarization mode dispersion. The light inside fibers is polarized, and this means that we have two different linearly polarized states, and they have different refractive index. So the index of the perpendicular component doesn't equal the index of the parallel component. And what we've done is we've arbitrarily chosen some axis in that fiber to be the axis that we're measuring parallel and perpendicular to. So we have polarized light entering that fiber. Okay, and a single pulse may occupy both different polarization modes in that fiber as it propagates, leading to, again, a dispersion. This one is a dispersion because the index itself depends on the polarization mode. Okay. In the same way that we could overcome loss with an antenna, we can overcome pulse spreading. With an amplifier, I meant, we can overcome fiber loss with an optical amplifier. We can overcome pulse spreading a couple of different ways. The first way is to use low dispersion fiber. We're interested in that 1300 nanometer window because of that fact. At 1300 nanometers, or very close there, the dispersion actually goes to 0 for optical fiber, for glass optical fiber. And that offers a great opportunity to get away from the effects of pulse spreading. We'll see it can lead to other problems, but that's one way we can do it. We can also, I don't know why it's not on my list here, we can do dispersion compensation. We'll talk about that later. But basically we can include what's called a dispersion compensation module. A DCM, which through a variety of different techniques can have the opposite dispersion as the fiber. So for example, you can make special fiber with negative dispersion relative to standard fiber. Okay, so dispersion does have a sign. This delta tau could be either positive or negative, indicating that longer wavelengths either have a higher or a lower propagation speed in the fiber. And so we can create fiber with the opposite sign of dispersion of normal fiber and include a short length of that to compensate. Or we can have various types of optical elements that through tricks of phase manipulation can compensate dispersion. Okay, we'll study that in a system level example later on in the semester. But we can use dispersion compensation modules to compensate for dispersion. We can also, sort of the ultimate is to do an OEO regeneration. OEO stands for optical, electrical, optical. And in this case what we do is we have a receiver and another transmitter. So we have a receiver and a transmitter back to back. Okay, and so we start off with an optical signal coming in, we have an electrical signal in the middle, and then we end up with an optical signal going out. So we detect reform and retransmit the signal. And if we've gone ahead and done this, if we do our OEO regeneration before the bit error rate deteriorates, then it's great because our receiver then has very low bit error rate, and then at the transmitter we create a perfectly brand new clean signal again. And so with OEO regeneration we really can have arbitrarily long fiber optic lengths as long as we keep each length short enough that our bit error rate is very small. Okay, so that's sort of the ultimate. OEO regeneration is very expensive though, and in general we're preferring to use optical amplifiers along the way to boost the signal strength to create very long links rather than doing OEO regeneration. Okay, that's it for these two slides. Thanks.